Bismillahirrahmanirrahim. Assalamu alaikum. Today we have a ninth lecture of the discrete structures. In the previous lectures we have studied and discussed the logic and predicate logic, quantifiers, and we have also studied the applications of logic into digital circuit designs, Boolean algebra, and also we have studied some universal and existential quantifiers. We shall see the applications of universal and existential quantifiers in the next topics. For example, in the number theory and the method of proofs, we shall also use the universal modus ponens and universal model tolerance and we shall frequently use these universal and existential quantifiers. So today we are going to start a new topic, which is the elementary number theory, and after this topic we shall discuss the methods of proof. Before 2 or 3 decades it was an expression that number theory is this theory doesn't have any applications, but when the era of computers has been started, we have seen that number theory have tremendous applications in the encryption theory, for example, in the network security and many other fields of computer science. The number theory has many applications. So here we start with the very elementary level, the number theory. In this theory we manipulate the numbers, we play with the numbers. So in today's lectures we shall discuss what are the divisors, how we can divide a number by another number. We shall also discuss even numbers, odd numbers, or you can say integers, real numbers. What are the prime numbers? Prime numbers are also very crucial. We shall discuss some theorems of arithmetic, division algorithm, what is the greatest common divisors, least common multiple, and then what is the relatively prime numbers. Some of the things you have already studied, for example, what is the greatest common divisors, least common multiples, but here we manipulate what are the applications and how we manipulate the greatest and least common multiples. So firstly, what is the divisor? How we divide usually in mathematics and in logic. Let A, B and C be any 3 integers. If we can write A as a product of BC, for example, if we have 10 here, if we have 10, then 10 can be written as 2 into 5. So what does it mean? It means that 2 as well as 5 divides 10. Here we can say that if we can write A in terms of B and C, then B and C are said to divide or factors of A. Here 2 divides 10, 5 also divides 10. We say that 2 and 5 divide 10, or we say that 2 and 5 are factors of 10, and A is said to be multiple of B as well as of C. 10 is said to be multiple of 2 and 5. How we write it in the number theory? This symbol is usually used to denote the division or the divisors. How we write 2 divides 10? For example, 2 this symbol 10. What does it mean? It means 2 divides 10. Here we can write B divides A, and is basically the conjunction operator here. C divides A. So symbolically A and B are integers and K is not equal to 0. Then if B divides A, this symbol means if and only if there exists an integer, you can say K is some integer such that A can be written as product of B and K. So the same example, if we have 10 can be written as 2 into 5. If we write 2 divides 10, then there exists, if and only if, here we write if and only if there exists some integer such that 10 can be written as 2 into what? Here 5. So 5 is that integer K here in this definition. So we say that B divides A here, and we write it as this: B divides A if and only if there exists some integer K such that A can be written as B into K. So this is how we write the division in number theory. For example, which of the following is true? 77 divides 7. Is it true? No, this is false, because 77 doesn't divide 7. Here the second, 7 divides 77. This is true, because 77 can be written as 7 into 11, sorry. So there exists some integer here 11 such that 77 can be written as 7 into 11. So we conclude that 7 divides 77. Sorry. 24 divides 24. This is true, because there exists some integer such that we can write 24 is equal to 24 into 1. So 1 is here basically that integer. 0 divides 24. This is false, because 24 cannot basically be written as 0 into some integer K. Is there an integer A, K here, such that we can write 24 equal to 0 into some integer? Is this true? No, this is false. So this statement is false basically. Again, also the 24 by 0 is undefined in mathematics. You know, this is basically, you can write it as infinity. 24 divides 0. This is basically true statement, because 0 can be written as the product of 24 into 0, because here 0 exists as an integer such that 24 into 0 is 0. So 0 by 24 is basically 0. So this statement is true. So I have discussed all the solution of this exercise here. Next, how we can find that how many positive multiples of a number are less than some other number. For example, how many positive multiples of 15 are less than 100? One method, which is simple and basic, that we list all the multiples of 15 which are less than 100. For example, 15, 30, 45, 60, 75 and 90. These are all multiples of 15 which are less than 100. So how many are multiples? There are 6 multiples. Now this method is only useful when this number is small. But there are situations where we need the multiples of some number which are less than some big number. For example, here, how many positive numbers of 15 are less than this? So here one method is just list all the multiples of 15 which are less than 100, but here if we start listing the numbers, the multiples of 15, it will take a long time. So we need to develop some algorithm or some method by which we can simply find the multiples of some number which are less than some other number. So here if we say that 15 divides some number which is less than 100, for example here the last number is 90 which is less than 100, so 15 divides 90, what is this? What is the answer? If 15 divides 90, then we have 6, because 90 can be written as 15 into 6. So this is the 6, and here we have again the 6. So how can we find the multiple of 15 which are less than 10 lakhs? So we find a number which is immediately less than this number and which is also divisible by 15. So that number is usually we can find easily 99999 and 0. Here we have 0, means we write here 99999 and 0. So this is the immediate less number of this number than this number which is divisible by 15. If we divide this number by 15, the answer is 66666. So there are 66,666 multiples of 15 which are less than 1,100,000, you can say. So in number theory, how we write it, in general the number of d multiples less than n is given as this. There is a number m belongs to z plus is set of positive integers, such that d divides m and m is less than n. So this is how we can find the multiple of some number which are less than some other number. We find the integer m which is immediately less than or equal to n, such that d divides m, and the answer of this division are the multiples of d. So here one more thing, that here we have the equality in this sign, m is less than or equal to n. When the m is equal to n, when this is true, if this number, because here this number is not exactly divisible by 15, if it would be if it would be some number, for example if we have 90 which 15 divides completely, 90, here we have 90, then the answer is 6. So if this number is completely divisible by d, then we can take m is equal to n. Now next is the divisor theorem. What we state in this theorem, if we have three numbers a, b and c which are integers, then we have these three results. If a divides b and a divides c, this implies a divides b plus c. For example, if we 2 divides 8 and 2 divides 10, this implies 2 divides 8 plus 10. So this result is universally true, or you can say that this result is true for all integers. So here we can see that if 2 divides 8 and 2 divides 10, obviously 2 4s are 8 and 2 5s are 10. 2 divides 8 and 2 divides 10, then 2 divides also 18. So this is the first statement, the first result of this theorem. The second result is this: if A divides B implies, or then A divides B into C. What is this? This is basically you can say, you can take this example. For example, if 17 divides 34 implies, if 17 divides 34 implies 17 divides 34 into 10. So what does it mean? If a number divides some other number, then the same number divides the multiple of the same number here. So if divides B implies A divides B into C. C is basically, if we multiply B some other number which is an integer also, then this result is also always true. We have another result, this which is called the transitive property of division. If A divides B and B divides C, this implies A divides C. For example, if we have 24 divides 72, if you take some simple example, if 6 divides 12 and 12 divides 144, then 6 divides 144. So this is basically called the transitive property of the division. So we shall prove these statements. Now the first statement is, as you know, A divides B and A divides C implies A divides B plus C. Suppose we say that basically this is the hypothesis and this is the conclusion in the conditional statement. You know, this is basically P implies Q. To prove this statement, we suppose the hypothesis is true, and we shall prove that the conclusion is also true. So we suppose here A divides B and A divides C. Then by definition of division, we can write B as a product of A into some integer m, and similarly if A divides C, then C can be written as A into some integer n. Here we have written this and this by the definition of division. Then by adding B and C, we get B plus C is equal to B is AM and C is AN. So we write AM is equal to AN, which is A, we can take the common A outside, and A is, we can write A into M plus N. Now if we take M plus N, some other integer K, because M is an integer, N is an integer, so sum of two integers is again some integer. So we write here it as B A into K. Now if we see here, B plus C is written as A into some integer K. So what does it mean? It means A divides B plus C. So we have supposed that the hypothesis in the conditional statement is true, and we have proved that the conclusion is also true by using some definitions of division. So similarly we can prove the other two statements. If A divides B implies A divides B into C. So how we prove such statements or such conditional statements? We suppose that the hypothesis of these conditional statement is true, and we prove that the conclusion in this conditional statement is also true. So we suppose here A divides B. If A divides B, then again we can write B as a product of A and some integer m. Here we have written it by definition of the division. Now if we multiply both sides by c, b into c is equal to a into m into c. This is into. Now if we take up m into c, some other integer k, as k integer, so b into c can be written as a into k. How we can write k? As we know that m is an integer, c is an integer, and product of two integers is again some other integer, so we can write m into c some k. So now we see that b into c can be written as the product of a into some integer. What does it mean? By definition or the division, that a divides b into c, so which is the conclusion. So we can say that by supposing that hypothesis is true, we have proved that the conclusion is true. So this whole conditional statement, this is true, and this is true for any integers a, b, c. So this is basically the universal statement, or you can say that this is a general result. The third is a divides b, and we have conjunction here, b divides c. This implies a divides c. So here we have this as a hypothesis and this as conclusion. We suppose that the hypothesis is true, means a divides b and b divides c. Then we have to prove that a divides c. So again, if a divides b, then b can be written as a into m, and b divides c means c can be written as b into k. So if we put the value of b in this expression, then c can be written as b a into m into k. So here we can write a into m into k. So m into k, if we suppose m into k, because m is an integer, k is an integer, so product of an integer is again an integer. This is another result. So m into k can be written as n. So what we have seen here, that c is written as a product of a, c is written as a product of a into some integer k. So what does it mean that a divides c by the definition of divisibility? So the conclusion is also true. We have proved that the conclusion is true. Again, this is called the transitive property of the division. So we have these three results now. So and these three results are basically the very basic results of division. Now the next is some definitions of integers. What is an even integer? Because we shall frequently use even integers, odd integers, prime numbers. What is the composite number? So by definition, an integer n is even if it can be written as the product of 2 into some integer. Or you can say that an integer is said to be even if it is the multiple of, it can be written as the multiple of 2. And what is an odd integer? An integer which can be written as this: n is equal to 2k even integer plus 1. For example, here if we have 16, this can be written as 2 into 8. So 16 can be written as multiple of 2, so 16 is even. Now the odd integer, for example 17, this can be written as 2 into 8 plus 1. So here this is not basically the dot, this is this represents the multiplication here. So 17 can be written as 2 multiplied by 8 plus 1 in this form. So any integer which can be written in this form is called odd integer. So what is prime number? First of all, the prime numbers are usually greater than 1. 1 is not a prime number. The numbers greater than 1 could be a prime number if it satisfies this property. An integer n is prime if and only if n is greater than 1, and for all positive integers r and s if this n can be written as product of r and s, then at least one of r or s is 1. So how we interpret it? For example, we have 3 as a n. Then 3 can be written as 3 into 1 or 1 into 3 in the product of two integers. So here we can see that one of these two integers is 1. So the integers which can be written in this form but at least one of r or s is 1 means there are no factors of these integers. So such type of integers are called prime numbers. For example, we can see 2 is also a prime number. We can write it as 2 into 1 only, or 1 into 2, and 5 is 5 into 1 or 1 into 5. These numbers can be written only in this form. So such type of numbers are called prime numbers. Another example, if we take 4, the 4 can be written as 2 into 2. Now here none of the number is 1, so this is not a prime number. So such number is called a composite number. So what is composite number? An integer n is composite if and only if n is equal to, n can be written in the form r into s for positive integers r and s, with r not equal to 1 and s not equal to 1. So the composite number can be written as two positive integers, product of two positive integers, none of which is equal to 1. For example, the number 4, number 6 can be written as 3 into 2. So none of 3 and 2 so 6 is a composite number. For example, we see in detail what are the prime numbers. A number, we can see another definition of prime numbers. A number n greater than or equal to 2 is prime if and only if it is divisible by 1 and itself. This is another definition of prime number. For example, if we take these numbers and we locate which of these are the prime numbers. 0 and 1 cannot be prime numbers because in the definition the prime number is greater than 1 or greater than or equal to 2. So 2 is a prime number because 2 can be written as a product of 2 into 1 or 1 into 2, as we have seen in the previous slide. Or the only number which divides or which are factors of 2 are 1 and the 2 itself. So such type of numbers are basically prime numbers. So the previous definition and this definition are basically equivalent, but we are saying them differently. So in the previous example we have mentioned that n can be written in the as a product of two integers r and s, one of which must be 1. This is equivalent here in saying that the number is said to be prime which is greater than or equal to 2 which is only divisible by 1 or itself. What we have said in the previous example, this is exactly same as this, because here we have seen that 2 is prime and the factors of 2 are 2 and 1, means 2 is divisible by itself and 1, or 3 is divisible by itself or 1. This is what we are saying in this definition. So 2 is a prime because 2 has factors only 1 and 2, or 2 is divisible only by 2 or 1. Similarly, 3 is divisible by 1 and 3 only, so 3 is a prime number. But 4, 6 and 10, here I haven't written the 10. For example, we have 10 also, then 4, 6 and 10 are not prime because 4 is divisible by 2 also, 6 is divisible by 2 and 3, 8 is divisible by 4 and 2, and 10 is divisible by 5 and 2, because these numbers are not divisible by 1 and themselves. So 9 again can be written as 3 into 3, none of which is 1, so this is not a prime. What does it mean that the not all odd numbers are prime? It is not necessary that if a number is odd then it is a prime. As an example, 9 is not a prime. You can take other examples. For example, 15 is an odd number which is not prime. You can say 21 is an odd number which is not prime. So it is not necessary for a number to be a prime that it is an odd number. Now, a theorem of arithmetic, or in the number theory, which is a fundamental theorem of arithmetic, what it states that any number greater than or equal to is expressible as a unique product of one or more prime numbers. As a unique means there doesn't exist some other expression of that particular prime number, of that particular number. For example, if we take these examples, 22 can be written as 2 into 11, or this can be written as 11 or 11 into 2. The places of the numbers can be changed, but this expression is unique. This is basically equal to 2 into 11. There are no other prime numbers which expresses the product of 22. So here we say the statement, any number greater than or equal to 2 is expressible as a unique product of one or more prime numbers. So 22 can be written as the product of two prime numbers. There are no other prime numbers which can be used to, you can say, decompose 22 into the product of prime numbers. So 100 again can be written as unique expression. 100 has a unique expression in which the prime numbers are multiplying. So one prime number can arrive more than one time in that expression. This is allowed. So we can write it as 2 power 2 into 5 power 2, 100. So this 100 has this unique expression of the product of prime numbers. Similarly, we can take 12, we can take 17 here. As we have seen here, any number greater than or equal to 2 is expressible as a unique product of one or more prime numbers. Here 1, what does it mean? 1. If the given number is prime, for example 17, then 17 will be expressed as 17 only. We cannot write here into 1. We cannot write here 1 because 1 is not a prime number. So be careful when you write an integer or a number into the product of prime numbers. Please do not write 1 in this expression, as 1 is not a prime number. So that's why we have in the definition it is given that expressible as a unique product of one or more prime numbers. So if the given number is prime, then it is written simply as, for example, 3 is 3. So this is the unique expression of that number which can be expressed in terms of prime numbers. So this is the theorem. We take some other examples. The 100 expression of 100, 641 is a prime number, so the only expression which can be given for 641 is 641, this number and this number 24. This is the unique expression of the product of prime numbers which can be, in which this number can be expressed. So as earlier I told you that the prime numbers can be repeated, but we cannot write here a composite number or 1. So every number has a unique expression of the product of prime numbers. This is the fundamental theorem of arithmetic. Now another result which will be used frequently in the subsequent lectures. So this is a result: if n is composite, then its smaller prime factor is less than or equal to square root of that number. If n is composite, then its smallest prime factor is less than or equal to square root of n. What does it mean? If we have, for example, 9, it can be written as 3 into 3. So here n is 9 and we have expressed 9 as a product of prime numbers. Now you can see that the smallest prime factor here is 3, which is less than or equal to square root of 9. So this is basically 3 is equal to square root of 9. So this is what we are saying in this result, that if n is any composite number, then its smallest prime factor must be less than or equal to its square root. So how to prove this result? Basically, in detail we shall study the methods of proof. How many methods are there to prove a result or a theorem? So one case we have studied in the conditional statement, that how we can prove a conditional statement to be true, P implies Q. We suppose that this hypothesis is true and we prove that the conclusion is true. This is basically the direct method of proof, and we shall study in detail in the next lectures when we shall discuss the methods of proof. But here we have used the method of contradiction. In this method of proofs, we suppose that the result is false, means what we have to prove is false. Then in this result we have to prove if n is composite, then its smallest prime factor is less than or equal to 1. This is what we have to prove in this result, and we suppose that this statement is false or wrong, and then on the basis of some definitions and mathematical identities or mathematical results, we shall prove that what we have supposed is basically a wrong supposition, and then when we conclude that the statement which is supposed to be false is true. So this is basically the method of contradiction of proving statements, and we shall discuss it in detail in the next lectures in the topic methods of proof. So by the method of contradiction, we suppose that the smallest prime number or the prime factor is greater than square root of n. We have to prove this is less than or equal to n. And what is the negation of this? This is basically greater than square root of n. So then by the fundamental theorem of arithmetic, we can decompose n as the product of prime numbers, where p is prime, q is prime, x is any number. It may be prime, it may be composite, but we can write n as a product of two primes and some composite. Now n can be written as p, q, x, and x here can be, it could be a prime number, it could be a composite number. Even if x is a composite number, then x can be written as a product of primes, for example r into s and so on. So we have applied here the fundamental theorem of arithmetic, but not completely, as we have x, we have not mentioned here that what is x. X, we have told here, is some integer. It may be prime, it may be composite. If it is prime, then this expression will be unique by the fundamental theorem of arithmetic. If x is some composite, then further we can decompose or write x as a product of primes r and s. So where p and q are primes, and we have supposed here that the smallest prime factor is greater than n square root. So p and q, if they are prime, then they must be greater than square root of n. So therefore we can write n is greater than n into n square root of n into square root of n into x, because here if we see that n is equal to p into q into x, and p is greater than basically n square root. If we replace p by n and q by square root of n, p by square root of n, then n must be greater than here. X remains the same. So now this is basically equivalent to what? This is n. So n is greater, here we have greater than, here we have equal. So this statement becomes, or this statement becomes n is greater than nx. This becomes n is greater than nx. So if we leave x here, because n is greater than the product of two numbers, then both numbers must be less than n. So we can conclude here n is greater than, which is impossible, because any number 7, this cannot be greater than 7, because n is any composite number, and a number cannot be greater than itself, which is impossible. So what we have supposed is false. Basically what we have supposed here, we have supposed that the smallest prime factor is greater than square root of n. Now this supposition is false, because there is some problem here. We have arrived at a conclusion that n is greater than n, which is impossible. So we conclude that what we have supposed is false. And if it is false that the smallest prime factor is greater than square root of n, then what will be true? Then the smallest prime number will be less than or equal to n. This statement will be true, and hence the result has been proved. So this is basically called the method of contradiction to prove a statement. I once again repeat that in this method we suppose that what we have proved is wrong, it is false, and by using some basic definitions of mathematics and basic results, we arrive at some result or some situation which is impossible. then we conclude that our supposition is basically not true. If our supposition is not true, then the result which we have proved will be true. So next is an example of the above theorem of this result. If we have two numbers which are composite, 139 and 143, which we have to prove whether these numbers are prime or not. How we shall proceed? How we shall prove that these two composite numbers are prime or not? We shall list all the prime numbers which are less than square root of these numbers. For as we have proved here in this lemma, if n is composite, then its smallest prime factor is less than or equal to n. Now list all prime numbers up to square root of n, means square root of 139 and 143. So 143 square root, what is the square root of 139? As we know that the square root of 144 is 12, so the square root of 139 is approximately 11 point something. So the number which is the integer which is less than the square root of 39 is 11, is the 11. So we check all the prime numbers which are less than or equal to 11 to prove that whether 139 is a prime or not. Again, also for 143. All the prime numbers which are less than 11 are 2, 3, 5, 7 and 11. So we check first for 2, whether 2 divides 139 or 143 or not. 2 doesn't divide 139 and also 143, as 139 and 143 are not even numbers. Now how to check whether 3 divides some number or not? There is a result for this. If we sum up the digits of the number 139 and the resulting number, if it is divisible by 3, then this number 139 is divisible by 3. This is another result in mathematics, in number theory, which holds for the division by 3. Any number is divisible by 3 if it's the sum of its integers is divisible by 3. So to check whether the given number 139 and 143 are divisible by 3, if we sum up the integers of 139 and 143 and the resulting number, if they are divisible by 3, then the whole number 139 and 143 are divisible by 3. So here 139, 1 plus 3, 1 plus 9 and 1 plus 4 plus 3, this is 13 and 8. These both numbers are not divisible by 3, therefore 3 doesn't divide 139 and 143. And now we check 5, whether 5 divides 139 and 143 or not. And you know that 5 divides only those numbers for which the last number at the end. For example, for 139, if we have at this place 0 or 5, then that number is divisible by 5. If not, then the given number is not divisible by 5. For example, if we have 125, here we have 5, this number is divisible by 5. If we have 100, we have 0 here at the end, so this number is divisible by 5. So only those numbers are divisible by 5 in which the last number is 5 or 0. So in the given numbers 139 and 143, the last digits are not 0 or 5, therefore these numbers are not divisible by 5. Now 7, we check the 7. As we know 140, because 7 2s are 14 and 0, so 140 is divisible by 7, so neither is divisible by 7, because 139 is 1 less than 140 and 143 is 140 plus 3, so these two numbers are not divisible by 7. Another result of number theory we will use here to check whether the given numbers are divisible by 11 or not. How to check? If we write the given number as 139 and we place alternative signs between these integers, for example, first we start with plus, we put minus, then we plus, and then so on, and we simplify this expression. Plus 1 minus 3 plus 9, what is this? This is 7. If here the resulting number, the result of this is 0 or a number which is divisible by 11, then we say that the given number 139 is divisible by 11. This is another trick, or you can say result in number theory, which can be used to check whether a given number is divisible by 11 or not. Similar reasoning we have applied on this 143, 1 plus 1 minus 4 plus 3. Now this becomes 0. As I have told you that if the resulting number is 0 or divisible by 11, then we say that the whole number 139 or 143 is divisible by 11. So here this expression, this simplification gives us 0, so we conclude that 143 is divisible by 11. So what we have concluded here, that 139 is prime because 139 is not divisible by any of the prime numbers which are less than the square root of 139. But 143 is a composite number, as the 11, which is a prime number which is less than the square root of 43, which divides 143. So the number 143 is a composite number. This is how we can check by using this result and the fundamental theorem of arithmetic to check whether a given number is a prime or not. Next, we start the division. What we have studied earlier is the divisors. Now we start the division. In early classes, you remember that how do you perform the division of two numbers. You divide the numbers like this, in which you know this is divisor, this is quotient, and this is dividend, and this is the remainder. So, and we write the dividend, this 117 is equal to the divisor, the quotient plus the remainder. We can write the dividend in this form. So in number theory, if we have two numbers, for example D and A, and we say that D divides A not if d divides completely a, then we can write a in terms of d into some integer. If d doesn't divide completely a, then we write like this: d a is equal to d into some integer q plus the remainder, which is the remainder here. We note here that this remainder must be less than the divisor, means r here must be greater than 0, because if r is 0, then d divides completely a. So r must be greater than 0 and less than or equal to, sorry, this could be greater than or equal to 0, and this must be less than the divisor d. If r is 0, then d divides completely a, means if we have 3 divides 15, then and we have 0. In this case, the remainder is 0. If the remainder is 0, we say that 3 divides 15 completely, and we write it as this. And if we have 2 divides 11, then 2 5s are 10, and the remainder is 1. In this case, 2 doesn't divide 11 completely, and we write it as this. Here the remainder must be greater than or equal to 0, less than the divisor. So now I give you the division algorithm, how we divide the numbers. Let a be an integer and d be a positive integer. There are unique integers qr with r is less than, you can say r belongs to 0, 1, 2 up to so on, less than the divisor. How we can write it as r belongs to 0, 1, 2 up to divisor minus 1, because if it is equal to the divisor, then again d divides completely a. So we can write generally the division algorithm as a is equal to d into q plus r, where a is the dividend, d is the divisor, q is the quotient, r is the remainder. So I recommend you to see in the book of Susanna Rosen the proof of this division algorithm, which is very obvious. You can understand it easily, and this is called the division algorithm. Now example: what are the quotient and remainder when minus 11 is divided by 3? We can write minus 11 into this form. Minus 11 is equal to 3 into minus 4 plus 1. So what is the quotient? Quotient is minus 4. And what is the remainder? Remainder is 1. So how we write the quotient? Quotient is minus 4, and we write it as minus 4 is equal to minus 11 div 3. Basically, if we divide minus 11 by 3, we get minus 4 as a quotient, and we write it as this. And remainder, how we write the remainder? So in this case, what is the remainder? Remainder is 1, and we write remainder is equal to the dividend mod 3. So this is basically the notation. We shall see, or we shall discuss it in further detail in the next lectures. Note that the remainder cannot be negative here. The remainder cannot be negative, consequently the remainder is not minus 2, even though this, as in definition we have discussed that r here must be greater than or equal to 0 and less than the divisor. So r cannot be negative. Even minus 11 can be written as minus 11 is equal to 3 into minus 3 minus 2. But here the remainder is negative, So by the definition of division algorithm, we cannot write minus 11 into this form because here the remainder is coming as a negative, but in the definition the remainder must be positive, and this is greater than or equal to 0 and less than the divisor. So be careful about it when you write this expression, this form in division. Now, what is the greatest common divisor? You have studied in early classes 7th, 8th that the greatest common divisor is a number which divides both a and b, but this number must be biggest which divides both a and b. So by definition, let a and b be integers, not both 0. If this is the necessary condition, if one of these is 0, then there will be a problem. We have to investigate the cases. The greatest common divisor, or we say that highest common factor, you have studied in early classes that greatest common divisor is also called highest common factor of a and b, or we write it as GCD of a comma b, is the biggest number d which divides both a and b. So we can say it a and b are said to be GCD, and another example or another definition of this is the greatest common divisor is GCD of AB is the smallest number which divides any x dividing both a and b. Means if there is some other number which divides both a and b, then greatest common divisor divides that number also. So this is basically the equivalent form of the definition of the GCD. For example, what is the GCD of 11 and 77? So the greatest number, the highest common factor between 11 and 77 is 11. And what is the greatest common divisor between, or the highest common factor between 33 and 77 is basically the 11. Similarly, between 24 and 36 and 24 and 25. Here you can see that in the fourth part, the GCD of 24 and 25 is 1. Means there is no other number which is the common factor of 24 and 25. So the highest common factor or greatest common divisor of 24 and 25 is 1. Such type of numbers are called relatively prime. As in the definition here, a and b are said to be relatively prime if GCD of a and b is equal to 1. So they don't have any common prime divisors. So once again, the relatively prime numbers are those numbers whose GCD is equal to 1. Now, what is the pairwise relatively prime numbers? If, for example, if we have numbers a, b, c, d, then these numbers are said to be pairwise relatively prime if any two distinct numbers in the list are relatively prime. For example, if we take a and b, these both are relatively prime. If we take a and c, these are relatively prime. If we take b and d, any two numbers in the given numbers must be relatively prime, means that their GCD must be equal to 1. For example, if we take this set and we have to write a subset of this set in which we have pairwise relatively prime numbers, means if we take any two numbers in that subset, these two numbers, those two numbers must be relatively prime. So here If we take first we start by prime numbers. Here 17 is a prime number, we write 17 because if you have a prime number then it must be relatively prime to other numbers if it doesn't divide that other number. So if we take 17 and if we take 15 here and 169 and 28, these are four numbers in this set which are relatively prime because GCD of any two number in this set may be 17 or 15. This is 1. GCD of 17 and 169 is also 1. GCD of you can take 28 and 15 is also 1. So any two numbers, if you take any two numbers, the GCD of these two numbers must be equal to 1. Now in this set we have not written 21. Why? Because if we take the GCD of 21 and 15, what is the GCD? There are common factors which divides both 21 and 15, which is, for example, 3. 3 is basically the greatest common divisor which divides 21 and 15, so we cannot write 21 in this set because 21 is not relatively prime with 15. Similarly, if we write 44 then in this set, then 44 and 28, the GCD of 28 and 24 is not equal to 1. So 44 and 28 are not relatively prime. Similarly, we can take another set, this. In this, every member in this set is relatively prime with each other. So the pairwise relatively prime sets are those sets in which any two elements are relatively prime. Now what is the least common multiple? As you have already studied, but here we revise this. The least common multiple. The least common multiple of two numbers, or we say it in the short form LCM of AB, is the smallest number m which is divisible by both a and b, or equivalently we can say LCM of two numbers a and b is the biggest number which divides any x divisible by both a and b. Means if there is another number whom a and b divides, then LCM must divide that number. So these two are equivalent definitions of the least common multiple. For example, we take LCM of 10 and 100. So what is the least common multiple? Least common multiple of 10 and 100 is obviously the 100, because 10 is a factor of 100, therefore the least common multiple of 10 and 100 is basically 100. In the second example, if we take the least common multiple of 7 and 20, or 7 and 5, basically is the 35. Now if we take, this is basically the biggest number which divides any x. If we have basically the LCM of 7, 5 is 35. Now if we have some other number x, for example 70, then this 35 also divides 70. If we take x as a 70, then this 35 divides also the 70. So LCM is basically the biggest number which divides any x which is divisible by both a and b. So if we take x as a 70, and the LCM is basically the biggest number which divides 70. So these two definitions are basically logically equivalent, or you can say them equivalent There is a relation between LCM and GCD. This is basically a general result in which we say that LCM of any two number AB is basically equivalent to the product of those numbers divided by their greatest common divisor. We can write it as in this LCM of AB is equal to A into B divided by GCD of AB. So we have to prove this result. This result is valid or true for any two integers. So we abbreviate the things. We write GCD of AB as a G and factor A and B using G. A is equal to GX, as here G is the greatest common divisor, then G must divide A and G must divide B. So A can be written as G into X and B can be written as G into Y, where X and Y are relatively prime. So this is obvious basically. If G is the greatest common divisor and if G divides some number A, then the quotient here, basically this is divisor, then the quotient basically X and Y must be relatively prime. Therefore A into B divided by GCD of X Y can be written as A can be written as GX, B can be written as GY, and GCD of AB is basically G. So one G will cancel with one G and we are left with G into X into Y. Now we can see here that GXY, G into X into Y, as GX is A is basically G into X and B is basically G into Y. So A must divide this whole number and B also divide this whole number, G into X into Y. So as here note A and B both divides GXY. On the other hand, let M be divisible by both A and B. We take another number which is divisible by both A and B. So MG is divisible by both X and Y because M is divisible by A and B and A and B are divisible by G. So it is obvious that M divided by G is divisible by both X and Y because A can be written as G into X and B can be written as G into Y. So as we have told here, as we have discussed here, that X and Y are relatively prime, then they don't have common factors, prime factors, then by the fundamental theorem of arithmetic, MG must be divisible by X into Y, because M by G is divisible by X, M by G is divisible by Y, then MG can be written as product of X and Y. So therefore if M divided by G is divisible by XY, then we can write then we can say that G into X into Y must divide M, which shows that the multiple of A and B is bigger than G into X into Y. So by definition, GXY can be written as this A into B. Basically here we have multiplication not dot. A into B divided by GCD is basically is equal to LCM. This will be the LCM, and LCM of A B is equal to A into B divided by GCD of AB. For example, if we take LCM of 10 and 15, what is the LCM of 10 and 15? Basically the least common factor of 10 and 15 is 30, and GCD of 10 and 50, greatest common divisor of 10 and 15 is basically 5. So we can write here 10 into 15 divided by 5 is 30. So the above result is valid if we take any two integers, as we have taken here 10 and 15. So This theorem is very useful in the number theory, and we'll use this theorem also in the subsequent lectures. Now, the importance of for the importance of number theory, you can consult this website and you can see that the number theory has tremendous applications in the encryption algorithms and many other branches of computer science. For today we stop here, and the summary of today's lecture: we have studied the divisors, prime numbers, and some even integers, odd integers, and composite numbers. We have studied some basic results and theorems of the number theory. We have also discussed the division algorithm and greatest common divisors, LCMs, and the relatively prime numbers. In the next lecture we shall continue this topic, the number theory, and we shall prove some other important results of number theory. Allah Hafiz.